sections is that they say it could be you know, a square, or it could be a circle, or a triangle, or many things like this. But would you like us to do one more of these to start out, or just move to the next kind of grouping of questions, which are rotations about the axis?
Maybe we should do one to just start out and then we can move over.
Okay, sounds good. So let's do, let's go with, let's say y equals e to the x, and we're going to do, we'll just do squares. And we're going to go from 0 to natural log of 4. So the e to the x curve looks something like this. It rises a lot more, but the square, like this is a square. This is an example of square. What that's its side, and so the side length here is e to the x.
Okay.
And then the area of the square, and it's sometimes good to draw it. The bottom is the e to the x, but then this is also e to the x. All right. So when you want to find the area of a square, you take base times height. I mean, you know this, but sometimes in the course of doing this, you may forget that you just add the exponents.
Oh yeah, I was going to say 2ex.
Yeah, and you just got to be careful with that. So now you're going to integrate this from 0 to, let me get the right numbers. Sorry, get a little more room here. We're going to integrate from 0 to natural log of 4. E to the 2x, that's the area. Dx gives you the volume of one of these pieces.
Okay.
And that's literally it. Once you come up with the area formula, you always stick a dx next to it and use the limits of integration.
So then it's just e to the 2x evaluated at ln 4 and 0, right?
There's a little more here. If you were to do it kind of fully, u would be 2x and du would be 2 dx, and you would divide both sides by 2. So you would end up having a 1/2 out here as part of your integral. And if that's not clear, we should maybe review that. But
yeah, so wait, is that just like chain rule?
Yes. When you take the derivative of 1/2 e to the 2x, you do get back to the original, but it's because of the chain rule, because the 2 multiplies the 1/2 to get back to that.
Okay. So then it's
kind of like this in some ways. The integral of e to the u du is e to the u over u prime. But that doesn't work for everything. It just works for when there's like a 2x in there.
okay. So then it's e, so 1/2 e to the 2 l and 4. But the ln and the e cancel, right?
After you move the 2 up here to the exponent.
What do you mean after you move it up?
You have to, this becomes the natural log of 4 squared, then they cancel.
Okay.
That's
4 squared, which is 16.5 of that, so 8.
Right.
Minus 2. No, e to the 0 is 1, so 1/2.
Yeah.
So yeah.
Something like that. I mean, you'll get in a standard test, you would get one problem like that, where again, it could be any of these geometries, right? Square base times height, could be circle pi r squared. I mean, they do semicircles, they do right triangles, you know, equilateral triangles. There's so many options that we can't cover them all, but you're expected to then know them all. Maybe you can even ask your instructor, you know, which geometry they're going to use.
Okay.
Maybe they'll tell you, maybe they won't. But the next type of problem that we would do is rotating a curve around an axis. That's the next type that you're seeing here. So let's do that. And If you're okay with that, I mean, do you feel like we've covered this known
Yeah,
cross
I think,
sections?
yeah.
Okay. Okay. So the typical problem here is like, if y equals the square root of x, what is the volume for rotating? And they have to tell you which axis. We'll say the x-axis from 0 to 9. And you probably saw this, and we'll do some of the examples you were given in class, but you probably saw this, that when you rotate this around the axis, like you can visually get a shape of it if you want, but like I'm not going to emphasize that because it doesn't really matter to me what the shape looks like. It's just a like a recipe at this point.
Okay.
Sometimes they do ask you, but I didn't see that in your notes here. So when you rotate, and this is called the disk method, or C, I don't remember how you spell it, but disk method. And it's the integral from a to b pi r squared dx. The r, this is your r. The r is the distance from the axis to your curve.
Okay.
So your r in most cases is y, because this is y equals square root of x. So the y value you get from the square root of x. So we have everything we need to answer this problem, but the reason it's a disk problem is because there's no gap. Like when you revolve this thing, it's a solid disk. And you probably heard about the washer method.
Yeah.
And that's different. So if there's no space, it's a disk, and you got to be comfortable with that. So
like, how do you recognize that it's a disk method just from like looking at the problem though?
there's no gap between, like, let's say this is 0 to 9. There's no gap between.
What do you mean by a gap?
So let me draw something else here. So let's say we wanted to revolve x. I'm sorry. Let's say we wanted to revolve y equals x and x squared. So yeah, there's a gap between the axis.
Oh, like you mean like, so for the disk, it's like always on the x-axis basically?
Well, we could revolve it around a line that's there, but as long as there's no gap, no area in between. I'll show you, I will show you washer problems. After the washer problems ones you'll see more of, but this is the starter like thing.
Okay.
Like we'll do this one next just to make it clear, but yeah, I mean, this disk method has to be down really well.
Well, is it because there's only like one like line basically?
That's part of it. Yeah, that's one of the reasons, because it's just one curve. If we were to, but the problem is, if we were to ask to revolve around the y-axis, so this one's revolving around the x. If we were to revolve it around the y, do you see that there is a gap?
Like a gap between what?
This area and the axis that you're revolving it around. So this red is your gap.
Oh, okay.
And it creates, like, if you were at one of the applications of this, which is a very primitive one, is like making a pot or a vase or something like that. You have this inner region and outer region that you're revolving around. So I'll try to make it clear. I mean, like, we're trying to make it really simple. Like when you, so that, like, maybe that is why they explain what this looks like when you revolve this original thing around the axis. It would be like a flower pot that was completely filled in. Like it would be hardened on the inside.
Uh-huh.
Because there's no inner region, but a washer problem produces what we expect when we go to buy a flower pot, like an area to put the pot in the soil.
Gotcha. Okay.
So the mechanics of actually finding the volume are pretty straightforward. Once you identify your A and B, which in this case is 0 to 9, when you identify your R is Y, but we want Y in terms of X, it's the square root of X squared dx. It reduces to a problem that you already know how to do.
So wait, the 4, wait, that's a 9, right? Not a 4.
That's a 9, sorry.
Okay.
Yeah, 9.
So then you just do the antiderivative.
Well,
right?
you simplify a little bit here. So you would bring the pi out, and then the square root of X squared is just X. And then now you would find an antiderivative.
So X squared over 2 with the pi in front at 9 and 0. So then that's 9 squared is 81 over 2 pi minus, yeah, nothing. Just like that.
Okay, so the question that your instructor gave, I think maybe this will make more sense. So let's say you have a semicircle and it goes from -2 to 2. Okay, this is y equals the square root of 4 minus x squared. That produces this. And when you revolve this around the x-axis, it becomes a sphere. And the formula for a sphere is 4/3 pi r cubed. And the radius here is 2. So it's 4/3 pi.
Do they tell you if it revolves around the x-axis, or you have to know?
Yes, they have to tell you that. They
Okay.
absolutely have to tell you that. All I'm doing on the right here, also, I should have said this earlier, is that I'm just going to show us, we know what the answer is. The answer is 32 pi over 3.
Okay.
Now we're going to do it the way this disk method.
All right.
This is not right. Oh no, it is. Yeah, it is. I'm sorry. Yeah, that's good. So and I like to do this in every problem. You'll see me do this, and remind me if I don't, is I always like to try to identify the R. And I think that's pretty helpful. So like you literally draw it, and that way you know which axis it's from, so that it's clear. Okay, that's my R.
Well, R, like as in radius, right?
Yes. All the disk problems have a radius. All the washer problems have 2 radii, and we'll discuss that next.
Okay.
So the integral is pi r squared dx. R is really a function of x. It's really this thing up here, and we're going from -2 to 2.
Wouldn't the radius be like from 0 to 2 on the x-axis though? Why is it a vertical line?
Because we're revolving this whole curve around the axis. If you were to just go from 0 to 2, you would get half a sphere.
Oh, I see. Okay.
And there's not really a good like if you were to cut, I don't know how you cut like oranges or apples, but if you were to cut them into the sort of that quarter piece and revolve it, you would see you don't get the whole thing back. Like this gets you the whole fruit back.
Okay.
So the R in this case is this function here. So this is kind of a test to see if you're right in some ways. After you square it, if you don't get something that you can integrate, that's a problem.
Okay.
So that's you're like, well, is this kind of right? And they're not emphasizing the integration either, so it shouldn't be like really a difficult integration. It could, I mean, there are cases where it is, but the median case, like the one you expect to see as a student, is something you can do, and this one you can totally do.
So that's 4x minus x cubed over 3.
Yes, times pi.
Yeah.
From -2 to 2.
That's 4 times. Wait, it's the bottom minus the top. So
top minus bottom.
Yeah.
It's just like when you're finding area between curves. When you do area between curves, it's always the top function minus the bottom function.
Oh, I said bottom minus top, but I did it.
Oh, good.
Okay,
great.
so then it's 8 minus 2 cubed is also 8 over 3 minus pi -8 minus plus 8 over 3. Oh, so it's just pi times it once. Okay,
Yeah, the whole thing.
right. All right. So then it's 8 minus 8/3 plus 8 minus 8/3. So it's 16 minus 16/3.
Yes,
And
16
5
minus, and then 16 is 48 over 3.
minus 16/3. So then that's, yeah.
Okay, and let's go back up for the big reveal. See how it matches your formula.
Mhm.
Yeah. So I think maybe I told you this at one point. I was like, when you were doing like algebra 1 or algebra 2, I was like, when you get systems of equations, you can always solve them and check your answers, and like you can always know if you got the right answer. And that's actually mostly true here. Most of these you could actually use a formula to figure out if you're right,
Right. Okay.
but it's not, that's not, these aren't designed like that. And like a good instructor will like give you problems that you can't just get the answer and then kind of show the work and get the right number. But we verified what we already knew. The volume of a sphere of radius 2 is 32 pi over 3.
Cool.
Okay. We can also do problems with respect to the y-axis, and we should do one of those now,
Okay.
if you're okay with that.
Yep.
So let's make it a little bit simpler. Let's say x plus y equals 4. And we want to, this is bounded by the x-axis and the y-axis. And we're going to revolve around the y-axis this time. So it's probably a good idea to graph it. And it's here, you get this equation right there. Okay, and this is a disk because we're going around the y-axis and there's no gap between there.
Okay.
But your radius this time is this right here. This is your r. And since you're integrating with respect to the y-axis, it's the same integral, but sometimes instructors change this. It's pi r squared dy because you're integrating with respect to y. Now this one happens to give the same area either direction, or same volume. Sorry, same volume. I said area a couple times, but it's really volume. Just know that that does not always work out. Like you really have to do it the right way.
Okay.
It's like what I'm trying to say is, as you go through this, you may find that there are problems that it's easier to do one way or the other, but the instructor will specifically say, kind of just like systems, like you will solve using this method. You will use the washer method. You will use cylindrical shells if you do it.
Oh, so they tell you what method to use.
Or it's obvious from the problem, but sometimes they tell you like you have to do it this way, even though it's easier another way.
Gotcha.
Okay, so in this case, your r, you have to solve for x, which is a little bit awkward. X is 4 minus y. We're used to solving for y almost all the time. And notice I did not give you the bounds of integration. You have to find them. You're going from 0 to 4. And that's just where it hits the y-axis.
Wait, you have to find. What do you mean?
Sometimes, yeah, sometimes you do, because it's bounded by the x-axis and the y-axis.
Like, you mean that like you have to find like the A and B and the.
Yes.
Okay.
Yes. And it sounds, at first you're like, well, no, I can't do that, but you truly can. It's not really impossible. It's just, you
Gotcha. Okay.
you'd rather not. Okay, so in this case, we're going from 0 to 4. put the pi on the outside. R is 4 minus y squared a dy. There are two approaches here for integration. One is to use a u substitution. Another is to expand 4 minus y. They both work. Just have to pick which one you like.
So that's just foiling if you do expand.
Yes.
Okay, I'll do that. So 4 minus y times 4 minus y first 16 4y minus 4y plus y squared. So then 16 minus 8y plus y squared.
That's right.
Yeah.
Okay, so you got to integrate that 16y 4y squared plus y cubed over 3.
Okay, so then that's, let's see. 16 times 4 minus 8. Wait, yeah. Minus 4 times 4 squared plus 4 to the third over 3. 16. 4 times 16, 64. Pi 64 pi over 30. Yeah. And then that's your answer, right?
That's your answer. Yeah. And you know, you start out with kind of a nice 1/2 base times height, but your volume is more.
Will they ask you to like identify the radius on the picture?
No, but this is like one of those Matthewisms that is really helpful. And I found students like it, especially when we go to washer method, because you have to identify 2 radii.
But isn't the radius just always what they give you, like your x value there?
When it's a disk method, yes. Except, and this is where, so I want to just like, I think it's worthwhile to give you a few more examples here. This changes when the it's a slight variation on the same problem or different problem. So let me give you an error. Let's say y equals x squared. Y equals -1 is what we're going to revolve around.
Okay.
And it's also a boundary. So I'm not sorry, I'm not writing out the complete question, but it's the region bounded by these. But we're also going to revolve around -1. Okay, so you know, in short here, and I got to give you some, it's this curve. We'll just go from 0 to 2. We'll go from 0 to 2. And it's like, you're used to this being your radius right here, which is y, which is the x squared. But now we're tacking on a little bit.
Oh, okay. So it's, I remember this from class. It's like +1.
Yes. Okay, so there's a bit more here. So it's integral from 0 to 2 pi. Your r, though, like you said, is x squared plus 1, but you have to square it.
Yeah. So then so you do you foil that, right?
Yes.
1 times x squared is 1. So then that's first 2. No. Fourth. First outside. Squared plus x squared plus 1. Let's do x squared plus 1 times. Okay, so then that's x to the 5th over 5 plus is it 2x cubed over 3? Don't you just,
yeah.
Okay.
So it's 1/5 x to the 5th.
plus x, and then all times pi at 2, 0. So then that's 2 to the 5th. Oh, 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16, 32. 32 fifths plus 2 times 8 over 3 plus 2. 32 fifths plus 16 thirds plus 2. So then common denominator is 15 times 3. 96 5. 80. 15, 30. So then that's 80, 30, 206 over 15 pi.
Very good. All right, so I've got to show you one more problem, which it's probably the last kind of, it is the exception to something we said earlier, but it's the only type that you might see. So we've looked at a graph like the square root of x. Okay, and if I want to take this area, I'm sorry, where I've only given you one curve and I've said the x-axis, but I change the revolution to, like, let's say it's the line y equals 3.
Okay.
We now have what is called a washer problem.
So the gap is from the
Yeah,
one,
because
two,
there's a gap
right
here. And
there.
I don't want to do this one first, but I want you to see that just because I gave you one. I mean, that's not technically, that's your second one, but if there's a gap, it generally becomes a washer problem, even if you have just one function.
Okay.
And so we can do some of those now if you're okay with
Yeah.
that. All right. So as I mentioned before, kind of the starter problem here is I gave you two curves. I tell you y equals x, y equals square root of x, or x squared, something like this. And we go from 0 to 1, and we go from the x, we go to the x-axis. Now, I do not have to tell you this. I don't have to tell you it's from 0 to 1. I could tell you the area between them, just like we're doing last time on Friday, where you have to find that. Okay, so again, how you find that is you set them equal to each other.
Okay.
And here you would probably square both sides. And then you would move over, you get x squared minus x equals 0, factor out an x, and you would get x equals 0, x equals 1. And you'd want to actually test those.
Like, oh yeah, okay.
All right, so now I'm going to graph what it looks like, and I'm going to really zoom in on this. Let's call this 1, 1 right here.
Okay.
And that's obviously, that's y equals x. But the square root of x, I believe, actually looks like this. So it creates this space in between.
Mm-hmm.
Okay, so there are now two radiuses. There is little r, which I'm going to do in red. And then there is big R, which I'll do in blue.
Why are they in different places on the x-axis?
The simple answer is because I don't want to overlap them, because but they're supposed to be in the same place.
Gotcha.
So it's the integral from a to b, and then I'll use colors here. Big R squared, if I can get them in here, minus little r squared, and then it's dx or dy depending on the type of problem you're doing.
So then it's pi integral from 0 to 2. What is the big R, it was root
Root x,
root
yeah.
x. So
Root
root x squared minus x, just x squared
Yes, dx.
dx.
Yep.
So then you simplify that. So then that's pi 0 to 2 x minus x squared dx. So that becomes x squared over 2 minus x cubed over 3 dx, or no, not dx, from 0 to 2. So that's pi times 4 over 2 is 2 minus 8 thirds. So that's 6, the common denominators. Times 3 times 6.
I think I may have made a mistake here. Because the answer is now negative, and that's not supposed to be.
Okay.
Let me go check something real quick.
I got the same thing. I got 12/6 minus 16/6, which is what, like?
Yeah, which is negative. Let me, I know what it is here, but let me just confirm this. Sorry for this. This is, get the right formula here.
Minus 4 pi 6.
Oh, and some books call this ring method.
Okay.
Yeah.
Here I got minus 2 pi over 3. That's so simple.
Yeah, maybe I graphed this wrong. Let me graph it. I did just make this up. I didn't really test it. So give me just a little flexibility or why. Yeah, from 0 to 1, that's big R is square root of x. Little r is y equals x. 1/2 x squared. That's 1/3 x cubed. 2 minus 8 thirds.
Why can't it be a negative?
Well, the volume, it's the volume of this region in here, so it's got to have some
Oh.
definite volume. That's nice. Sorry, it's volume with rings. Why is this working? There must be a mistake here in something that I am not seeing. But
Wait, why is it 0 to 2?
oh, that's why it's 0 to 1.
Oh, okay.
that is the reason why this didn't work.
Okay.
And the reason why is because it flips, and then there's negative areas, but
Right, and those, well, what was the purpose of finding the zeros?
to give you the bounds of the integral.
But don't they give you those?
I gave them to you, but they don't always give them to you.
Gotcha. Okay.
So this is going to change this quite a bit,
Right.
because this is going to be 1/2 minus 1/3, which is what I was expecting, which is 1/6 pi.
Yeah.
Hooray. Okay. All right. So now let me go back to your notes and see if I can work through one of the practice problems with you, if you've got one here. Yeah, here's a good one. Okay, y equals, it says the region between these two curves about the x-axis, so that the first step is to set them equal and figure out, if you don't have a graph, where they intersect here. So we'll subtract x from both sides, subtract 3 from both sides, factor, and x equals 2 and minus 1.
Okay.
All right, now we really should figure out which one is the top one and which one is the bottom one. And to do that, I mentioned this before, you can test a point between the two bounds.
So like 0,
Yeah, between
then
-1
y
and
equals 1 and y equals 3, so that one is that one's top. Yeah.
yeah, but you also, what you don't know, that and this is where I don't know how to tell you either how to do this, because really graphing is the only way, is you don't know whether there is a like a gap. You don't know if that was drawn really poorly. Sorry, let's go with like that. Like you don't, this one does have a gap. So it is a washer method, but I'm not sure how you,
if there's two. Oh wait, no, there's an exception. But if
it's possible that there is no gap, but I don't know what to tell you, because it's just one of those things that you know, you're probably going to have big R and little r almost always. I'm probably speaking from the wrong place.
like,
I mean,
you mean like but like usually if there's two like equations, it'll be a washer problem.
yes,
Okay, but there's exceptions.
there's yeah, as you know. So the integral here is from -1 to 2 pi, and then your big R squared is this x plus 3 squared.
And then x squared plus 1.
Yeah,
And
and we should carry through this integration just to continue working on this. As a reminder, a plus b squared is a squared plus 2ab plus b squared. That may
yeah,
save you some time on these.
plus 6x plus 9. Yeah, and then so then you got to simplify that, right?
Yeah. So these are going to be all negative.
So that's x squared. Oh no, you can do 2x. So x squared minus 2x squared. So minus 3x squared.
This is positive.
Oh wait.
And that's that one. So it's just minus x squared.
Minus x squared plus 6x minus x to the 4th plus minus plus 8.
Yeah. And we still haven't integrated yet. So you gotta like
So then minus x cubed over 3 plus, well, there's a pi out in front, plus 6x, no. X minus x to the 5th or 5, 8x from 2 to 1. All right,
yeah. So a nice simplification here would have been if your instructor told you like
0
or somehow, but like I understand that from here there's no more calculus. This is purely just evaluating numbers. And
so then it's 3 times -1 squared -1 to the 5th of 5, 8. So then that's -1/3. Oh wait. Okay, so 8/3 minus 1/3 minus 3 minus 1/5 plus 8. So then the 12, the 16, and the 8 combine. So that's 20, 16, 36, right?
you're talking about the 12, the 16, and the 8. Yeah, that's 36. Okay.
6, and then the -8/3 minus a 1/3.
It's minus 9/3. It's minus 3. Did you deal with the 3?
Oh, I forgot about the 3.
So there's plus 3. I'm sorry, minus 3.
Minus 3.
And then you got minus 32/5 minus 1/5.
So minus 33/5.
Yeah.
So then 36 minus 6. No.
It's 30. Yep.
Yeah.
And then so that becomes 150/5.
Pi.
So that's 117/5 times pi.
Mhm. That's not what we got on this, on the PowerPoint, I don't think.
There's no answer on this one. It's possible we made a mistake in the.
Wait, is this is the one that's.
It's not completed. It's.
Oh, I see.
So I couldn't tell you. I mean, it's.
I was on the wrong page anyways.
The main thing though, like is really this big R and little r. Like the integral is the integral, but you got to be able to identify these two components of it. And a y-axis one is kind of up next. That's our chart here. So let's just reuse kind of one we've already looked at, which is x plus y equals 4. X equals 4. So this region, and we'll go around the y-axis. So if I draw it, this is the x plus y equals 4. Oops, I needed one more line. Y equals 4. X equals 4. So we're revolving this region right here around the y-axis. So because there's a gap, it's a washer problem.
Okay.
This is your little r. This is your big R. So in the case of your big R this time, it's always the same value. Like the radius is the same whether you're down here or up here, because it's the distance from the y-axis to this vertical line. So your big R in this case is 4. It's that right there. It's 4 squared minus. And because we're doing it with respect to y, you have to solve this for y. It's 4 minus y.
What about the y equals 4?
That's just giving us a boundary.
Got it.
That's y equals 4. That's x equals 4.
Wait, and then the x equals 4. Wait, so how did you graph these?
So the x plus y equals 4 is the intercept approach. You put 0 in for y, 0 in for x, and you get the straight line.
Line, yeah.
And then x equals 4 is always a vertical line.
Oh, that's just okay. That's
always, yeah. And like there's more words. Like it would be
Wait,
well
so
written.
how do you know that the x equals 4 is the top one?
It's the vertical one.
Yeah, like the vertical. But like, why does that one go first?
Oh, because it's big R. Big R is the distance from the y-axis to this line.
Because it has a bigger
Yes.
distance from the y-axis.
Yes.
Okay. So then that is 16 minus 4 minus y, 4 minus y, 16 minus 8y plus y squared. Yeah, and then that becomes 8 minus y cubed over 3, 4 and 0. Oh, that's less. Okay, so then it's 4 times 4 squared, which is 16 minus 4 cubed, 64 thirds. 64 minus 64 thirds. Yeah.
Yeah, so I think that might have even been the same answer that we got before, believe it or not, for a similar problem. You tend to see these kind of answers and you get comfortable with how they look when you're doing this. What I was trying to explain up here is that they're going to do a much better job of telling you what the region is, and they're going to tell you which axis, and sometimes they give you the bounds.
What if you like don't know how to graph it though? Like, how would you know which one is the top one for this one?
You would do the same thing as we did before. You would pick a value between 0 and 4. Okay. And you like 2, and you would put it in for y. So here it would be x equals 4 minus 2, which is 2. And then here x is always 4.
So if you're revolving around the y-axis, you always solve them for x.
Yes.
Okay.
They don't always give them to you in x. Like you may have to solve them yourself. And so I think maybe for the last one here, like we'll set it up, but not integrate, because sometimes it's really hard to, a lot of time is spent integrating, but let's see if we can do it here. So here's, this is this problem where they don't tell you much. This is the region over here on the left.
Mm-hmm.
So the region is y equals 0. So that just means it's in the first quadrant generally. X equals 2.
Mm-hmm.
That's x equals 2. And then this 1/4 x squared, well, when you put 2 in, for x, you get 2 squares, 4, 1/4. You get, it's this point right here. So it's some sort of curve like that.
Why are you putting 2 in?
That because that's where it ends. That's where it hits. This is one of the boundaries.
Aren't you graphing 1/4 x squared though?
Yes, and that's why I'm putting 2 in to here to figure out where it hits on the, like what the y value is.
Okay.
But because it's bounded by y equals 0, it's this stuff down here.
Right. So then it's 2, well, pi with 0 to 2.
But it's about the y-axis this time. So it's from 0 to 1.
Oh, okay.
And then big R this time is 2.
Minus 1/4 x.
Except it's an integral with respect to y. So you have to solve this for x.
Oh, geez. Okay. So confusing. Squared.
Right.
So if it was respect to x, you would do from 0 to 2.
Yes.
Okay.
So there's kind of this progression, which I'll leave you with. There's disk. X-axis is probably the easiest. Disk, y-axis. Washer, x-axis. And then washer, y-axis.
But they could give you some where for the x-axis ones you have to solve them in terms of y too, right?
So more generally, they would say that this approach is for the horizontal axis. Horizontal, vertical. And the reason I'm showing you this is because we did one of each kind. We did more than one of some of these kinds, but it is good to identify the types,
right,
that you're dealing with, because they're all the same once you realize what the type is.
Okay.
Right. Well, that does take us to the end of our lesson today.
Thank you.
I've actually opened up some times tomorrow. Do you have, I know you've already scheduled out for the week, but do you want to move any of the lessons from later in the week to earlier? And if you said your test was on Wednesday or something.
The test is on Wednesday, so I might schedule one for tomorrow.
I can move it if you would like without just now, or if you want to text me, I can move it also if you want to do something tomorrow. I got 4 and 5 open tomorrow.
I think I want to keep the Tuesday one, so I might just schedule on your website.
Okay. Thank you so much. Hope you have a great rest of your day.
Thank you.
Bye now.
Bye.